All right. Hey, Phil.
How are you doing?
I'm all right. You?
Yeah, I can't complain. What's new? What's new with you?
What's new with me? Not a lot. Uh, Still working on my homomorphic encryption project. Just just go between my house and the gym.
Nice.
That's about it. What about you?
Yeah, I'm pretty busy these days. But there's right now there's a break. Because I was teaching in person for the first part of the semester, but now they have transitioned to online after Thanksgiving. In the next like week and a half before people go off to Thanksgiving or not, depending on what their plans are. And after which everything will transition online. There's like a sort of break for what they call semifinals. This term, I think
This
it's
is
to
new.
allow.
They didn't used to have this.
Yeah, there was no. Yeah, so I think this is only a one time or only for this year. Um, I think it's because some um, bigger classes are require either additional time or they would like to have at least some component of the final or some component of the final grade that is based on an in-person exam rather than you know um, off campus or take home exam, which would be the only possibility if the exam were to happen after
Yeah.
the Thanksgiving transition to online. So I think that's what it's for. That's what these semifinals are. They're basically like midterms, but they can count for much more. And this allows large classes for which it's difficult to organize. You know,
So no students will be coming back after Thanksgiving.
some students are just going to stay. For example, my graduate students are planning to stay. I think through Thanksgiving through December.
Hmm.
But if people leave, um, I don't know exactly what the modalities are. But in any case, there will be no in-person classes after Thanksgiving.
Hmm. And are there any plans for the spring semester?
Yeah, there are already plans for the spring semester. The spring semester will be starting a bit later. I think usually here the spring semester has been starting in January, towards the end of January, or maybe like 3 weeks into January. But this term, or next term rather, it will start in February. Uh, I don't know what the exact calendar is, but it's already available. So unless there are changes due to whatever changing situation, the calendar is already out.
Well, anyway, I guess I'm glad not to be part of any school right now.
Well, I have to say it's been. I mean, it probably depends a lot on what class you're teaching, but for me, it's been pretty good. I have to say, it's not really been too stressful or overly difficult. In the spring, I was teaching a topics class, and that was fairly, unproblematic. I was just teaching 100% online. But since it's a topics class, there's only a few graduate students who are attending. There was no homework. Um, the grade was based on a final project, which most people didn't take too seriously, but everybody was taking pass fail anyway, so that's not satisfactory, unsatisfactory. And this term, I'm teaching a graduate class. It's a bit, I guess, people really do need a grade, but it being a graduate class, it's not. There's not as many people. Number one, and I have a bit more leeway in how to organize the class.
Because I taught a topics class once. I forget. I guess I did have to give grades, but I don't think there was an exam or anything.
You know,
Anyway, so you are my first guest from the math world,
nice,
and
nice.
uh, I guess I want on my show to do some kind of discussion about math in a non-trivial way, non-superficial way. Not necessarily. It's not a lecture. It's just I don't know something that will I don't know listeners or viewers who are interested in math generally. What's going on? What is it really? sound like. I don't know. We'll see what happens. Um, so I mean, I know you from we were there 2 years at Cornell together while I was a postdoc. And you, what is your position?
I am an assistant professor right now. I've been at Cornell for about, this is my fourth year. Yeah. I started in 2017 in the fall.
Right, right, okay. Um, so what is it that why don't you just say, what's your background anyway?
Oh, yeah. So you mean mathematical background?
Any, just
Yeah. So I work mostly in probability on problems that are inspired by mathematical physics. Although, compared to, for example, my advisor and other people who say they're doing mathematical physics, um, I'm
who's your
really,
advisor?
my advisor was Michael Eisenman at Princeton, who was definitely, certainly a mathematical physicist. So his interests were very close to physics. He's actually a professor in the physics department as well as the mathematics department. And the problems that he sort of grew up mathematically at a time when math, at least the part of math that he was really interested in, statistical mechanics and field theory and um, physics, physics as in physics that was contemporary, that people really cared about, were sort of much closer. In the 70s and 80s, when the foundations of quantum field theory were already laid down, but when a lot of ideas about things like the renormalization group, so understanding some of the divergences that appear in quantum field theory, were still a hot topic in physics. At that time, mathematicians were also starting to try to understand how you can make sense of something. What does a quantum field theory mean, and how you could make sense of it mathematically. But this whole program that Eisman contributed to at the beginning of the 80s, as well as many other people in mathematical physics around now, the department at Princeton especially, that program has basically ground to a halt since then. So a lot of the ideas continued on in math, but physics, went a different way. And the gap now between rigorous physics, between rigorous mathematics, rigorous mathematical physics, and the things that physicists, especially high energy physicists, care about is very large now. Um, so, to come back to me, I am very much inspired by the work that Michael Eisenman did, but I'm definitely more interested in math for its own sake. Um, I'm I like physics, but it's more a side interest of mine. So the problems that I'm interested in, they do come, all of them, more or less from physics, but I'm interested in really the math behind them, especially analysis, so analytic tools. So analysis being like this rigorous version of calculus for people
Right. Well,
who
I
don't
think
know.
I've heard you give two talks. One was on I think percolation, or was it
Yeah, that's right.
summative
Percolation.
model in statistical mechanics? And then you gave another talk, the applied math colloquium on some differential equations.
Yeah, yeah.
And what unifies? So I mean, both of them have to do with mathematical physics, as you say, and you is your main area of expertise probability or analysis?
Yeah, I would say probability, but mostly with analytic tools. So probability is a very broad field, like all fields of math at this very, when you talk about algebraic geometry or number theory or analysis or geometry. Similarly with probability, it can mean things, and the tools that you can use to study it, um, study the problems in probability are very different. So there are parts of probability which are very much very combinatorial, very much about dealing with discrete structures and counting. There are parts of probability that deal with discrete models, but use not necessarily combinatorial tools, but even, let's say topological tools, or tools that are quite specific to that specific area of
What do you mean
probability, say for example
topological?
percolation. Yeah, so even topological tools. So in percolation, for example, a lot of the early some or a lot some of the early work, some of the foundational work, um, in 2D, but also if you try to go to higher dimensions where not so much is known, uses basic topology, even not so basic topology, or at least graph theory,
Maybe we
topology in
should
the form of graph theory.
say what's percolation? Something.
Yeah, percolation is percolation is the study. A percolation model is just a model on a graph where each either vertex for what is called side percolation or edge is present in the graph with a certain probability. Um, so really, your percolation model is just a probability probability distribution on the subgraphs of a certain fixed graph. The original formulation of percolation due to Hammersley and Broadbent and Hammersley was on the what physicists call the square lattice, which is a hypercubic lattice, or in 2D, just a square grid. And each of the edges of that square grid is either present or absent with a certain fixed probability P, and this happens independently for all the edges. So if you do that for the whole infinite graph, for each realization of all these random variables associated to each edge, you get a certain subgraph of Z2. This is independent or Bernoulli percolation, but especially recently, thanks to new advances in the theory, people have considered also various forms of dependent percolation where the edges are present or absent, not just independently of each other, but there can be some sort of either short range or even long range dependence between the edges. And so if you really want to be very general to the point of being almost useless, indeed, percolation is just the study of distributions on the subgraphs of a fixed graph.
And you ask like, what is the chance that there's a path
Exactly.
inside to
Yes.
another?
Perhaps what really characterizes percolation is that the type of questions that you're interested in are connectivity questions. So the basic question in percolation is whether there is an infinite connected component somewhere inside the graph. It turns out that in ZD, this is equivalent to whether the origin is contained in an infinite component.
So what is it that, okay, I have a whole bunch of questions, and what is it that connects what you were doing, say, with percolation or statistical mechanics with your work in differential equations? I know you were talking about the nonlinear Schrodinger equation.
Yeah. So what I was talking about was differential equations with random initial data, which now has become, especially in the last 10 years or so, has really become almost a standard part of the toolkit of differential equations, at least certain.
Not my toolkit. That's not what I understood as part of differential.
Yeah, so what I'm thinking of is, for example, some work of Martin Hare on stochastic differential equations, but also extensive and more, a growing body of work on dispersive or other evolution equations with random initial data. It turns out that a lot of the evolution equations, so when you try to solve the initial value problem for a PDE, when you have an equation with certain initial conditions, in the theory of PDEs, what often happens is when the equation is nonlinear, the solution may not exist for all time, or the solution may lose regularity in the sense that the initial conditions, after some time, the function that describes the solution becomes worse than the initial data to the point where you can no longer measure its regularity in the same space, we would say, as the initial data. But very often, or in typical situations, there are either guesses coming from physics or good reasons, even mathematically, to think that the situation is not generic, meaning that you can find some initial data for which the solution will not exist forever. You can find examples, sometimes even concrete, explicit examples that you can write down, for which the initial data starts out very nice, but if you start running the equation, you see it blow up. You see things no longer be nice after some time. But this is not the typical situation. Now, there are many different ways of making this statement about typical situations precise, and one of them is using probability. That is using initial data that is not just this specific bad example, but initial data that is chosen at random. Now, whenever we talk about at random, especially when we're talking about a big space, like the space of functions on some, you know, the space of nice functions on some domain, you really have to specify what do you mean by at random. You have to specify the probability measure. And by now, this is, as I said, this theory has developed a lot, and there are many different ways and many smart ways of choosing initial data. Smart in the sense that they lead you to results about the solution existing for a much longer time than you can prove if you consider all initial data, or perhaps even forever. But a big, an important starting point, an important like seminal series of article in this direction was some work of Bourgain, and also previous work before that of some Russian people like Zhitkov, and I think some people from the Russian school. One of them, I'm forgetting one of them, and these people were interested in specific types of initial data, and this type of initial data that they were considering was sampled from a measure called a Gibbs measure, and a Gibbs measure is something that comes from statistical mechanics. So if you're asking me what is the link between percolation and this work that I was talking about on partial differential equations with random initial data, is that the type of initial data for some problems later on, this developed a bit away from statistical mechanics. So the type of initial data that people were originally considering for these equations was initial data that they guessed based on analogies with statistical physics would be particularly well suited to the equation. So for the equation, there is a specific way to choose the initial data. It's chosen at random, but not just in any random way. It's chosen according to what's called a Gibbs measure. And this concept of
There's
Gibbs
a measure on some space of functions.
Exactly. In general, a Gibbs measure is just a certain form of measure. It's a certain type of probability measure that was introduced by Gibbs, um, physicist, famous American physicist.
Gibbs, Josiah Willard Gibbs had this
Exactly.
very
Yeah.
idea.
Exactly.
And
Not
people,
not the idea to apply this to PDEs, but the notion of Gibbs measure, I believe, is due to him. It's definitely named after him.
no, it's definitely named after him. I just wonder in what context. No one was talking
So
about
he
measures
again,
in the 19th century.
yes, but so the measure, the mathematical concept of measure is just a formalization of ideas like mass and volume and length and
Sure.
area. And it was found by Kolmogorov in the 30s that also probabilities are properly, or in almost all situations, are adequately described by the same notion. So just like we can ask for the proportion of the mass of an object that lies in a certain subregion of this object, we can ask what is the probability of a certain event. And what Kolmogorov said is what you're really doing there is, when you're asking for the probability of something, is you're thinking about some abstract space of all the possible events, or maybe some slightly more reduced space of subsets of a given fixed space. And when you're asking what is the probability of some event, is you're asking what is the mass, or what is the area, or what is the length, or what is the volume of a certain subregion.
Of
That's
course.
the link between measures, and I think Gibbs would probably have called such a thing an ensemble. He would have said to each of many different configurations, we associate a certain probability. And
Right.
if you have a subset, or a subset of this, of all the configuration space, you can associate of the configuration, so of the ensemble, you can associate to it a certain mass that's described by this Gibbs measure. He indeed would not have called this a Gibbs measure, but he would have called this a Gibbs ensemble.
Maybe presumptuous, perhaps.
An ensemble here.
Yeah, but I think most we can imagine think of a space of configurations if it's finite, or if it's space with infinite dimensions. A little trickier to think of in the space of functions. Might be
Yeah,
infinite dimensional.
that was one of the big, I guess, achievements of the early 20th century, or the first third or so of the first half of the of the 20th century is making sense once people realized, thanks to Kolmogorov, that the proper way to do probability is to think about measures on abstract measure spaces, to think of this abstraction of the notion of volume. They started trying to make precise various notions of measures on function spaces. And since I know that you really like the history of, of mathematics,
Right.
one of the people who were made perhaps the fundamental contributions to this is Norbert Wiener, was probably one of the most important, certainly one of the most important early mathematicians, but it's often said that he is one of the first really important American born and bred mathematicians at a time where when he was working, it was in the 1930s, most of the mathematicians that we still remember now were either were born and studied in Europe. But he was born in the U.S. and he did all of his work. He spent all of his working career at MIT. And what he contributed, to come back to our discussion, is really clarifying um, how this notion of probability could be made sense of in infinite dimensional spaces, including spaces of functions. So his big contribution, what he's best known for, is um, his study of what is now called Wiener measure, or equivalently the distribution of Brownian motion, a
Right.
certain
So definitely
random
by that
function.
time,
Yeah.
he was putting measures on spaces of functions. Some might take issue. I've heard many people say maybe Josiah Willard Gibbs should be considered the first American mathematician,
Yeah, so I think this
even
really
though he was
depends
a
on what
chemist.
you call a mathematician. I think um, during the 19th century, the notion of what we consider a mathematician definitely changed. And this is related to this bifurcation between mathematics and physics that I was talking about. If you look at a lot of the people that we remember from the 19th century, certainly in the areas that I am interested in, like probability or analysis, the people who are remembered for their contributions, and even somewhat later, if we think of von Neumann, they had very deep connections and a very deep understanding, and often even made fundamental contributions to physics as well. But in the course of the 20th century, I think this definitely changed. You have a lot of people who are professional mathematicians, and um, a lot of the people who were in the 50s called themselves mathematicians. If you look at what they did on a day-to-day basis, it looks a lot more like what we call a mathematician nowadays, somebody who's employed in as a research mathematician, either in industry or certainly in academia, than what Gibbs was doing. The type of proofs, for example, that you would find, the type of arguments rather that you find in Gibbs's work on statistical mechanics. He has this famous book, famously difficult to read, but also extremely important for all its ideas. This book on statistical mechanics. The type of arguments that you read in there are of a very different nature, I would say, and a different level of rigor than what Wiener was doing. Although there's certainly much to be said about Wiener's work as well, because he was also somebody who was interested not only in physics but very much in engineering, and a lot of his work
Really, I didn't know
was
that.
definitely not So he was very much interested in engineering. He had some contributions to engineering, to the theory of filtering and the theory of control, and he even had an almost
Right.
philosophical field that he calls cybernetics, that we would call something like control theory, mixed with AI, that he developed in a very famous book called Cybernetics. Um,
Really.
yeah, so he certainly was a person who understood applied mathematics very well, and as well as physics.
Well, this is some part of math and the history of math I don't know because probability is really not my field. Um, so what is it that what is like the big question in your field?
Yeah, so
Are you after it, or that's
I,
also
I,
something I want to
I'm
know.
contributing. I'm trying to contribute to a few areas of probability. I think in each of these areas you can think of one or two questions. Probability and related areas of percolation rather, and related areas of probability. So related areas related to percolation within probability have really played an outsized role in the last 10 or 15 years. There have been, I think, 2 Fields Medals given out for work related to percolation. Wendelin Werner and
Yeah.
Stas Smirnov both got the Fields Medal for work closely related to percolation. And so because of that, the perhaps biggest, most central question in percolation is also often mentioned when people ask what is the most important question in probability. And that question is the question of continuity in higher dimensions, continuity in 3D of the critical point. So if I had to explain exactly what that means, remember we talked about how in percolation, well, not exactly, but in vague terms, we talked about how in percolation you choose this random subset of the square grid, and you want to ask in this random subset, what is the probability that 0 is contained in an infinite component? The big not the big mystery, but the first realization by Broadbent and Hammersley is that this is a complicated function. It's a function that varies with the density, so it varies with the probability that you assign to each individual edge, either being present or absent in the graph. And as you increase this density, so this parameter, of course, the probability of 0 being connected in an infinite component is going to increase. This is, I think, intuitive, although it requires a bit of work to really formulate this precisely. And now the surprise is that this probability is 0 initially, because if each edge has probability 0 of being present in the graph, clearly you can't get anywhere from the origin, but it remains 0 even for positive densities until what is called the critical point, until a certain value after which it is positive. And the question is, the big question is this
You there?
function continuous? Is this a continuous function? Yeah.
You okay? We good now?
Yeah,
I think I'm drawing a so probability of each edge included, and probability that 0 is connected to infinity. You're saying it looks like this.
It looks like this. So in 2 dimensions, we know that it looks like this. In particular, the graph connects at this value PC. There's no jump. We know also that away from this critical value, where suddenly the probability becomes positive afterwards and is 0 before that, we know that away from there, the function is very nice. It's analytic in addition to being increasing. It's a very nice function. But the question is it continuous? So if you're exactly at this critical point.
Oh, so we don't know. Here, what I drew is stuff we don't know, and
we know it in dimension 2. We don't know it in dimension higher than or equal to 3. So that is probably the biggest question. The reason why I would say there's not as many people working on this as perhaps you would want to is not because, as perhaps happens in some areas, people are not concentrating on the right thing, but because thanks in part to this new, these new ideas that were started by Smirnov and Werner, and also I think Lawler and Schramm deserve mention. A lot more is known in dimension 2, and by a lot more, it's not just trivial things. Much more than just continuity, which was known quite a bit ago, even before Smirnov. We can describe what is called the scaling limit of not only percolation, but a whole host of 2-dimensional models, including models that physicists cared about much more than percolation, like the Ising model.
Right.
And the description of that scaling limit, so the description of what you see when you zoom out, has been a huge success for mathematical physics, to the point that it's one of the very rare instances where mathematicians came up with an object, came up with a new idea really that physicists didn't even suspect. What often happens in mathematical physics is
which object are you talking about? SLE?
Yeah, that's SLE, and more generally the scaling limits of these 2D models based on various instances of SLE. Usually in mathematical physics, the usual story is that physicists will say they've basically understood a situation. This can be discussed because sometimes the arguments that you see in physics textbooks, a mathematician would say don't necessarily make sense. The objects are not necessarily well defined, but
Yes, I've had that problem.
still, after the fact, after mathematicians, if they ever do, when they come around to really proving, they get to the point where they're able to prove to their own satisfaction, understand the situation the way it's described in physics textbooks, which is not the typical case. Usually we're not able to reach that same level of precision in the description of the guesses. And usually mathematicians are just after physicists' guesses. Physicists make these marvelous guesses and then mathematicians work for years to make sense of them. And sometimes, as I said, the setting is not obvious at all, how you could even make sense of what they're talking about. Physicists have an amazing imagination. So you sometimes need to understand the proper mathematical objects to even make sense of the statements that they're trying to make. But once you forget this, mathematician's pride, basically you have to admit that the physicists they had guessed more or less what would happen. For example, they were not surprised necessarily by what you would see in simulations. They were not surprised by experiments. They had stories which, even though they're not mathematically rigorous, allowed them to make predictions, perhaps only qualitative predictions, but predictions nonetheless.
Right.
And those are rarely, if ever, modified, except for at the edges, in edge cases by mathematicians. But SLE is an example where this usual story does not hold true at all. Really, mathematicians came up with something that was not even suspected by physicists, and that really became part of even the physicist's toolbox, at least in 2D. Of course, real physics or a lot of interesting physics does not take place in 2D. So that doesn't settle the question. But to narrow down on what your original question was, this continuity in 3D is perhaps, in higher dimensions, is perhaps the most important problem in percolation. The reason why it's not solved, or why there are not so many people working on it, is number one, it's hard, and number two, there is still, or there has been in the last 10 years, a lot to be done in 2D. A lot of interesting, mathematically interesting, but also physically interesting math around percolation.
So it's going to be, I'm thinking it's going to be a totally different world in 3D as opposed to 2D, where
That's the expectation. There are some, if you think about statistical mechanics in 3D, it's not the case that there is nothing. There are various results, interesting results. They're nowhere near as detailed as what you know in 2D, but they're very interesting nonetheless. But the picture is much, much less complete than anything that physicists imagine. I think physicists even have they're starting to the last 10 years or so, maybe last 6 years, they have started developing a new technique called the conformal bootstrap, that supposedly, or at least to their satisfaction, allows them to solve a lot of these models or get a lot of information. And so far, mathematicians cannot touch this. And within statistical mechanics, percolation, because of its very, very simple definition, is typically that's step zero.
so
If you
this is
want to,
easier. The question you raise about continuity at the critical point in 3D percolation is easier somehow than solving the 3D Ising model.
certainly much, well, yeah, you have to specify what exactly you mean by solving. But yes, it is likely percolation is typically a bit easier than the Ising model, or in some cases much easier than the Ising model. And in addition, the question of continuity is not be said to be solving the model completely. Often when physicists say they can solve the model, at the very least, they would like to know the asymptotics, and perhaps quite exact approximations or quite close approximations to something they call the two-point function, which in percolation would be the probability that zero is connected to a large distance. And this in 3D is really connected to a point at a large distance, or the probability that zero is connected to a large distance. And this in 3D is very far from, the question of continuity is a much more basic question. It doesn't ask about the asymptotics, but zero is connected to distance n. It asks, does this limit go to zero?
Yeah.
And even that is not at the critical point. Even that is not known. But yes, I guess it is probably the case that once people figure out, and this is very often, once, this is very often the situation, this continuity question contains by itself, if it were just about this somewhat strangely defined function, it may not be so interesting, but we expect almost certainly, if you're able to prove this, you would need to understand much better what's going on in 3D percolation. So whatever techniques allow you to prove this would probably get you closer to an understanding of the sort of quantities that physicists would be interested in. Physicists don't really care about statements, the type of 0-1 statements or continuity statements. Those are too qualitative. They would like to know something that you can measure. Like percolation is really a very idealized model that at least in principle you could run simulations on, and you could look at numbers, not just whether a certain number is zero or non-zero, but really see on the graph what its behavior is.
So, are there physicists who work on the same kinds of things that you work on?
In percolation, certainly, yeah. In percolation, for example, one thing that I worked on in percolation that I've worked on quite a bit is the notion of chemical distance. Chemical distance just means the graph distance. How far, once you've removed all these edges, because you've depopulated a lot of the graph by this random process of eliminating a certain proportion of edges at random, you can ask whether things are connected, but once they're connected, you can ask how far are they in this new graph compared to the old graph. So for example, in the square on the square lattice, you can ask, so yes, in critical percolation, you
This
could
is
say
the
something.
minimum distance along the graph, or the subgraph that's left,
Exactly, the
right?
minimal, it's just a graph distance. For some reason, physicists call this the chemical distance, but this is something that physicists have worked on extensively, and it's one of the quantities in 2D percolation that despite the big improvements, the achievements in describing the scaling limit of critical percolation, it doesn't seem like SLE is, or at least so far, it doesn't seem like SLE is much help in telling you how this distance behaves. That's something that physicists have worked on. Now,
Even
of course,
even at the critical, or you say off.
especially at the critical point, especially at the off the critical point, it turns out that the distances are more or less, they remain more or less the same up to a certain, up to a constant. But off the critical point, at the critical point, sorry, if you're not off the critical point, so at the critical point, things are much less clear.
Huh.
So of course, now you can ask, what type of physicists are you talking about? Because there's a whole, I often think about something that's very interesting that to me is really a, personally, unlike many other mathematicians, I don't really have this grandiose vision of mathematics as something extremely deep and almost, an almost religious admiration for the structure of math. But within the context of the interface with physics, I think I do have some, certainly an admiration and I do wonder about how it's possible that people are able to understand each other who have such different visions of their fields. I don't even necessarily mean mathematicians on one side and physicists on the other side, but what I mean is think about a project like CERN, for example, the particle accelerators. If you think about the people who were working on those magnets or working on building those tunnels, those really engineering people, and then adjacent to those, the people who were on a day-to-day basis running the accelerator. And then adjacent to those, the people who were designing the experiments. And then adjacent to those, people who were more theoretical, but still trying to explain experiments by theory. And then, as you get further and further out, people who were, the sort of people you would find at IS were really fully theoretical high energy physicists who were trying to dream up theories. And then, across the hall from them, pure mathematicians.
Also, a
It's
lot of
very,
computer people have to deal with all the data and the.
absolutely, absolutely. It's very impressive how, first of all, it's very impressive when you come from outside. It's very surprising how a lot of the things that are considered, that's the consensus settled science and very clear, are really not so clear at all. That often depend on a lot of guesses, a lot of approximations, including all of the, big results that are not in doubt in any real sense, in the sense that nobody really thinks, okay, we don't know what's going on here. Um, in quantum field theory, if you come at it from a mathematical perspective and you ask, how is it that this thing really works, even though we don't even really know how to define things properly, um, that's very mysterious, and it's even more mysterious when you realize that when you ask some physicists who are definitely, I would say, sometimes much more creative and intelligent than mathematicians, they do not even see what the problem is when you tell them, okay, well, this quantity in quantum field theory doesn't even seem to make sense to me. Like, say, a functional integral, they'll just say, well, I don't see what the problem is here.
Yes,
And
I definitely had that experience myself communicating with physicists. I tried to learn both math and physics as an undergraduate, and somehow hit a wall with physics. I went into math, and then just a few years later, trying to communicate with some I took a course in statistical mechanics in the physics department, and I don't know, there was some quantity this guy called the order parameter, and I just at some point couldn't follow. Is this a number? Is this a function? Is this a I don't know. I didn't know what anymore was going on. Um, they do think about these things differently. I guess I was just in the context of your field and these problems, though. I mean, I don't, I can imagine you need, here's one paradigm. Imagine like the physicist works with materials, makes measurements, observes that there's, a critical point, observes that there's some behavior of some, whatever, in some material. Guesses, it puts forward the mathematical model. Well, once there's a model, once there's a kind of, imagine we should study something like percolation or the Ising model. At this point, to see the ramifications of that model, you need a mathematician. That is all math at that point. You need to use the structure that you've defined and see, can you extract information from that? And you need mathematical tools to do that. I don't know how you're going to do that without those tools. Does that
I
make
think
sense?
I, I think you need mathematical tools, but I think mathematics means different things to different people, including to mathematicians and physicists. I think if you take them, if you take the physics class, what you just said, the few sentences you just said, now we've set up everything, now let's do some math, you could hear that in a physics class, in a class where most of the students, for example, have never really heard of the mathematical underpinnings of Hilbert space theory. Yet in a quantum mechanics class, the professor would say something like, okay, now we've set up the problem, now we're going to do some math. And then within 5 minutes, the next 5 or 15 minutes, the students would hear about Hilbert space theory, they would hear about the spectral theorem, they would hear about all sorts of tools, which if you develop them fully mathematically, would take you weeks to really do properly. If properly were interpreted the way a mathematician would think about it. But they would be interested more in symbolic manipulation and arguments that, even though they're mathematical in the sense that there's no obvious logical contradiction, they are not at the level of rigor of what a mathematician would accept. They are math in the sense, again, of being symbolic manipulation and combined with logical arguments and physical intuition. And for them, this is math. And more often than not, it leads them to correct conclusions, or at least conclusions that are not so wrong as to get them in trouble. And when they do get in trouble, then they go back and say, okay, well, that's that. We should have justified a bit more carefully. In contrast, a mathematician is concerned with logic. He's really concerned with the structure of the symbols and not just things that seem plausible physically. The question for a physicist is always, well, why not? If it sort of makes sense physically, let's just do that manipulation. Let's treat this function, or let's treat this matrix, or let's treat this theory even as if it were differentiable in whatever parameters, including the dimension. Let's tailor expand and see what we get. A mathematician would spend, perhaps years trying to make sense of what does it mean to tailor expand the theory in the dimension. And that, I think, is the big difference. Both of them would definitely say that they're mathematicians, and physicists are, I would say, not only are they proficient, but they're even, yeah, they're extremely proficient users of, including very advanced mathematics. Advanced in the sense that if you took this math, you took those names, you took the terminology of, say, algebraic geometry or whatever blow-ups or brains or whatever that they use on a day-to-day basis, and you went into a math department and you asked, what do I need to learn to really understand these things mathematically, you'd be given a stack of books this high, but yet, master's students or even undergraduate, and not exceptional undergraduates, just undergraduates in physics, have no problem manipulating them, these objects.
No, I don't think that's true. That
No, I
wasn't
think
my experience.
no, I absolutely think it's true, because just like in math, if you want to be a graduate student at a top department in physics, you have to have at this point, you have to have at least familiarity with a lot of graduate material in in your field, and to properly set up, for example,
Gee,
general relativity. If you wanted to properly set up the equation, even just the basic equations of general relativity, to set up this problem in math, you would need much, much more knowledge than anything that you see, even as a math student, if you do a standard curriculum. And so it is absolutely the case that a student in physics who is doing computations in GR, they're doing computations with, they're manipulating objects that
to
if
state the
you
equation, I
look
think you
at,
need some differential geometry.
yeah, exactly, you need some differential geometry, and the differential geometry class that you take, even if you're an honors student in math, it will be a class taught from, say, for example, Do Carmo's curves and surfaces, and it will be about submanifolds of R3 or curves in 2 dimensions. So you will certainly not
Perfectly good
see.
thing to learn about.
You yeah, absolutely.
You want me to
I
read the
100
curvature?
I
Is
want
that
yeah, I 100% agree. And this is not a criticism of Duchamel. I think it's probably much more important even to really understand this very well and to understand covariant and contravariant tensors in 4 dimensions. However, you will, in such a class, you will not get to those objects, and those are the objects that you would need, in addition to a lot of graduate analysis, if you wanted to, for example, set up, the evolution problem and say anything about non-static solutions of the Einstein equation, which, you know, in an undergraduate class on general relativity, the professor is freely going to speculate and make, um, you know, intuitive arguments based on. So that's what I mean. I
what?
agree I agree that once you've set up the problem, what all you need is math, but math means different things to different communities, even different people.
Okay, I guess that's certainly true. And everything you said is, I guess, I know examples of what you're talking about the differences in the approaches of physicists and mathematicians. Because we're touching on a big topic here. I guess what I was trying to get at is, I think there's a difference. What's nice about this field of statistical mechanics, especially in some of these lattice models, is that unlike quantum field theory, which you were mentioned earlier, which is probably where I hit the wall in my education in physics, and I never understood that. But there are some areas which you seem to be talking about where physicists come up with a model and a way of dealing with things, I think largely derived by analogy. Some of these functional integrals, for example, and the things they wanted to do, which, to take the symbols literally, turns out mathematically they don't make sense. And you could play a whole game as to try to how to make sense of them. But at least this lattice models, they're well defined. This makes perfect sense, right? And now once you take that and you say, well, is this actually the right model? Like, does this model show the behavior in the Ising model? Is there this point of non-analyticity? with temperature, or for percolation, that there's this critical probability, and what can you say about the probability that zero goes to infinity, there's some path. All of the work, I feel like the work of understanding that model and knowing that it actually applies to physics is the work of a mathematician. You really need that's a mathematical problem that requires mathematical tools, mostly analytical tools. And would you agree with me, physicists, for a lot of the tools that they have, and they certainly know Taylor series and Fourier series and differential equations, and if they do GR, they know differential geometry. Uh, I feel like physicists don't do as much analysis.
Yeah, I think part of that is that part of the reason for that is that analysis, especially um, yeah, I think analysis, especially the analysis of PDEs, as it's practiced within mathematics, is it's a sort of soft subject, not in the sense that mathematicians usually mean, because mathematicians often talk actually about hard analysis versus soft analysis, and hard analysis involving a lot more estimates, and
What is soft
almost
analysis?
soft analysis would be functional analysis where you use tools that are not so much based on hard estimates and inequalities, but more on almost algebraic
Yeah, yeah.
definitions.
I
But
agree with that.
even hard analysis, the results that it gives are often very qualitative. So I know a lot of PDE people would be, they would bristle at this because they'll say, no, I'm proving estimates and these C alpha norms and these Bessel norms or whatever. But if you have to explain to a physicist what it is that you're doing, the end result is, yes, you derived all these estimates, but what you're saying is this function is smooth. This type of, and maybe you can even measure its smoothness. This type of statement is typically not of interest to physicists. Statements about existence and uniqueness for physicists, unless they're really accompanied with very concrete, measurable quantities, are not of interest to physicists. So
Well,
again,
can I,
yeah,
so here's how here maybe is a simple example. Suppose a physicist, maybe even Newton, or I don't think it was Newton, but Fourier, he writes down an equation, the heat equation, which he calls the heat equation. The simplest equation he could write down to describe, heat based on some conservation principle, or, you just take Newton's law of cooling and write it out in space and time, okay? Here's this equation now. Ut is equals k Laplace u. Now, what does it mean to the physicist, as you say, that they're not, you say the physicist not interested in existence and uniqueness, but that's the whole thing. I mean, there's nothing, to my mind as a mathematician, you've written down an equation that we have very good reason to be interested in, but we're not certain. There's no certainty that this equation actually describes anything just yet. To my mind, what you have to do now is you take that equation, now that's a mathematical object, it deals with abstract mathematical things, and you have to answer, like, under what conditions will you have a function that solves that equation? And of course, that deals with the problems of existence and uniqueness. And existence and uniqueness don't show up in a vacuum either, because depending on how what you mean by what constitutes a solution, the larger you take a space of functions in which you can consider what is the solution, the easier it is to prove existence, but the harder it is to prove uniqueness, and vice versa if you restrict so much. And so really what you end up doing with that equation, what it means to solve the equation and to prove existence and uniqueness of a certain type of function under particular kinds of conditions, is really that proving the regularity, is proving those estimates, all the hard stuff. How does the solution depend on the initial conditions, on the boundary, on whatever? And that somehow when you can prove the right regularity theory for that equation, that's what answers that question of existence and uniqueness, and that something is smooth. And now you actually have, solutions. Now you have something that you can go back to the world of physics and say, like, here's the observed behavior that comes from math. Here's what we can say about that there exists
Yeah, I
solutions
think
and
this. I really disagree with this. I think you don't have to convince me that it's of interest, and that if your primary interest is in the mathematical structure of things, this is the route that you would go. But for a physicist, just knowing abstractly that something exists or that it's unique, this is of no importance. In most cases, when a physicist writes down an equation, the way that the meta story would be something like this. They would write down the equation, and the fact that the solution exists is almost self-evident, because they would say, well, this is physics.
Yeah,
The
but
solution
I think
exists,
that's the perspective I think is totally wrong.
the solution exists just because it is describing some natural phenomena. If the solution
No,
does not exist, then maybe we set it up the equation incorrectly. Maybe the problem is there. And I absolutely
and
agree. And
that should really be a real concern.
there have been examples where mathematicians have been able to point out that there are non-existence results, or this equation doesn't quite make sense, or doesn't have uniqueness if you don't set it up correctly, and it's not so easy to set it up correctly. But these often come too late to be of any interest to physicists. And moreover, what physicists really are interested in is almost always fairly explicit solutions for which they can compute the long-term behavior, or at least in some approximation compute the long-term behavior. And that's what's of interest. That's why
Of course, but that will
often
follow.
analysis doesn't have that much especially analysis of PDEs has often not had as much to contribute to physics, back to physics, as perhaps other fields. That's
Yeah,
my impression.
I know that is the attitude of many people. I think this is a real point of disagreement here. I didn't know it was with you. I knew it was with physicists, because in my view, a lot of what you put forward as a model, you do not know at the outset that this is what really describes nature. It's really wrong to say, well, we know that there is a temperature, so there must be solutions to the heat equation. Wait. You just wrote down this heat equation, making a lot of assumptions so that you could write down, and you did the right thing because you wrote down the very simplest model that took into account the kinds of things, the kinds of forces that you thought were at play. Of course, there will be all sorts of other forces. You ignore all kinds of other things, and probably it's very smart to do so, because an equation that took into account all these other things will be a lot harder to solve, a lot harder to figure out what's going on. So you start by taking the simplest thing that you think has a chance of describing the behavior at the level you want to look at it. But then the question of whether that model actually does what it is that you hope that it does becomes a mathematical question in my view. It's no longer something you can't say, well, of course there's a temperature, and of course it doesn't blow up. Maybe of course it doesn't become, you start an oven and the sides of the oven are held at a certain temperature, that you shouldn't have 5 seconds in a temperature spike that's way higher than any place where you're heating it. Right, but that's a feature that you can see when you solve that equation. That comes out mathematically of that abstract model that you tried to write down, and it is the solving of that equation, in my view, that tells you in the end that that was that was the right way to talk about heat.
So I guess we're not. It's not so much a disagreement. I'm just describing the situation, the cultural situation, and I think these cultural differences are, as very often, they're justified to some extent by the facts. There aren't that many examples that we can point to where mathematicians analyzed some equations and went back to the physicists and told them, "Look, we did all this work, we got all the estimates, and what you guessed was really wrong." They exist. I do not I don't want to pretend that there are no examples, but these examples are extremely rare, and more often than not, in those situations, the obvious response that physicists can come back to are one of, well, there are many possibilities, but two of them are very common. The first is that what you're pointing out is an instance where the model clearly does not work. It doesn't work because we didn't take into account friction, for example. It doesn't work because we didn't take into account that, you know, at some point there are like finite size effects and you cannot really do a continuum approximation. Now you can go back and say, well, okay, this is sort of rewriting history. Now you're telling me that actually you knew that this model could not have worked. But that's a sociological response. It's not a response on the math. And then number two, the and you know, a related, I think a related objection that they often come up with is that even if you can give examples where things clearly don't work, these examples are examples that are artificial, that don't actually occur in real life. So they will tell you, okay, yes, for this equation describing, for example, you know, water or, you know, the movement of waves, you can find solutions that blow up, but that's because your initial data to start with was not something that we ever see in real life, or because the way you set up the equation. I think I would be the problem with I understand, I agree that it, if there were infinite time and if everybody had time, for example, to deeply, you know, study partial differential equations, they would realize the value of what sort of insight it can give you. But if you're a physicist and you're mostly interested in describing nature, and you look back historically at what happened, you don't have many examples where physicists were wrong because of a delta missing there and epsilon missing there, or
Yeah,
because they did not have a hard bound in any norm. I agree that
I
the
don't know if my
problem is
point is
that if you actually want to study, if you actually want,
long.
if you go back, you start, if you as one person, not as a part of, like, you know, the body of, you know, as somebody trying to advance the body of human knowledge and just trying to do research, but if you as one person, you try to sit down and construct for yourself a completely logically coherent version of physics, including, you know, including, you know, all these equations, and then you probably need to learn a lot of the math, and you probably need to know, for example, that these equations that you're writing down make sense. All I'm saying is that in practice, when you go to a physicist and you say, I have proved in 1,000 pages that the solutions exist for some time that is possibly incredibly small compared to any sort of timescale that you're interested in, they're not going to be impressed by this. It's not, of course, mathematically,
Can we just
of course, mathematically, this is this is more satisfying. And the few, and I think there are actually quite few, the few mathematicians who really think about how their analytic work connects to physics, how, you know, we really think physically. I agree that they can gain insight from this type of work, but I just think this is, I understand why physicists are not interested in it.
can we just actually I just need to go to the bathroom. I'll be right back. But okay, so to get back to what you're saying, so I certainly understand. It's I'm not making a criticism of physicists or their or I understand why they don't want to you know, have training in a whole different thing to do a very different kind of thing. I do nevertheless think I'm trying to try. I thought I've teased out, at least for myself, and I wonder what you think about what is the role of a mathematician in this kind of these models of physics. Maybe another example. I mean, you know, I forget now. I'm forgetting who it was. The one who observed the shallow wave that just propagated along in the canal.
Mhm.
And of course, it falls to someone, you know, someone wrote down this KdV, Korteweg and de Vries, I suppose. I guess I don't know the history exactly. Um, but the challenge there, once you write down some equation, the challenge was to have an equation given the model of, you know, functions that solve differential equations that exhibits that very behavior.
Yeah.
And that challenge, it seems to me, is one that is, even if a physicist could have looked at, what forces are going on if the canal is shallow, that you should include another term, because that behavior does not really happen simply. They wanted it. He wanted also to be nonlinear. It doesn't happen in the linear equation. You have, if, for it to happen in a nonlinear equation, I guess you need. That's the work of a mathematician, fundamentally. I think.
No, so I guess I disagree on this. I think Portovec and De Vries, I don't know if they were mathematicians, but what they actually did, and here it's a pretty good example that you're giving, because there is, on the one hand, the fact that if you look at the KdV equation, there are very explicit solutions that you can find using ODE techniques
I see.
that physicists completely master. Just like physicists, whenever they talk about GR, they don't try to set up anything in Sobolev spaces. They do reductions, reductions, reductions until they're down to an ODE that they learn to solve in undergraduate, and then they extrapolate from this one ODE, with say the Schwarzschild solution or the hydrogen atom, from this one very simple, exactly solvable or complicated, exactly solvable model. They extrapolate and guess. Like if you go back to you think back to say for example high school physics, you think about like this whole theory of orbitals that you were taught. Um, Proving any of this, mathematically justifying the theory of orbitals, mathematically justifying this, starting from the multi-electron Schrodinger equation, the multi-particle Schrodinger equation, is horrible. And I'm not sure that even perhaps at a qualitative level, I'm not sure that you could prove even say 75% of what you were taught in high school chemistry, this theory of orbitals. You could prove it even with modern technology. You could prove it, but how was it derived? It was derived by analogy from this one explicit solution.
Yeah,
Similarly, this whole theory of
I mean,
solitons.
from the hydrogen atom, you
Yeah,
can
exactly.
solve, and the hydrogen
If you,
atom and the Pauli exclusion, and that gives you the
Yeah, exactly.
periodic table.
Similarly, if you ever read any book and solitons are mentioned at all, probably if they do the math, they'll have an appendix where they derive the ODE solution of the Korteweg-De Vries
Okay, that makes
equation, and then they'll say, okay, well these solitons, that's all we need to know, and then from there they'll have a qualitative theory, maybe perturbative theory. After that, centuries later, people are still within math are still working on things like if they're doing that is at least adjacent to this initial story. They're working on like the stability of solitons. Can you have solitons not this? They're not exactly this initial this specific solution for the specific exactly solvable initial data, but can you perturb it and show that they remain a soliton for a while? What happens when you have interactions of solitons? The thing that physicists guessed just based on simulation and observation, or much further out even, they start asking how low regularity can the initial data be for the Korteweg-De equation. There's much more work within math on this type of question than anything that a physicist would be interested in. Now, don't get me wrong, I do think that if you are one, trained in physics, and two, really understand with a view towards physics all this work, this much later work within math, I do think it's a valuable perspective. I think your understanding will be epsilon above that of a physicist who's only trained in physics. But I think the return on investment is quite limited given how much effort goes into developing these mathematical techniques.
Certainly if it is just the case that we're asking different questions, because to me, if as you say, in the cases we've talked about, right, like, to me, as trained as a mathematician, it makes a whole lot of sense to be, given an equation, what's the theory of, can you prove existence and uniqueness in some space? If you're looking at these lattice models of statistical mechanics, like, can you prove, people thought, if there's a phase change, like, can you prove that as the temperature goes through some point, there's non-analyticity in whatever, it's some function. Can you prove the properties of that graph that I drew for percolation? Those are all completely concrete mathematical questions, and I just don't know how the physicist has access to answering them, except with mathematical techniques, which I think in what you're working in now are very sophisticated mathematical techniques. Now, what you're saying also seems to me that a lot of it, that's not what they care about. They're interested in answering some other kind of question. I don't know, that I don't know. I've never done experimental physics. Is there anything, do you know of anything in like statistical mechanics that's actually helped people, say, I don't know, work with graphene? There's a 2D material, or
So I don't know. I think within statistical mechanics and condensed matter theory, I do think I don't want again. I don't want. We started with this example of SLE. I don't want to discount the influence that mathematicians have had. I just think that generally the inclination from that you have as a mathematician from your training, also because a lot of mathematicians don't, after a while, don't study that much physics. They're not exposed to so much physics. They're not exposed to the culture of physics. Your inclination, and I think this is extremely valuable, and it can be extremely valuable, including if you want to really understand physics in a coherent way, in a logically coherent way. This inclination of trying to really make sense of every object that you encounter, make sense of it logically, have it have a precise definition. This is something that often can be almost counterproductive in physics. One of the great strengths and one of the reasons high energy physics is so successful, and one of the reasons it's so hard to learn for mathematicians. You described your difficulties with quantum field theory. I think a lot of people have seen it. It's because in the quantum field theory, you have a lot of objects that are not properly defined. And for mathematicians, this is a problem. But for physicists, it's easy to see how this can sometimes be an advantage. Because if you can assume that basically anything you encounter is a field and can be Taylor expanded or can be manipulated as if it were a smooth function, even though we know that in many cases this is not logically consistent, you're able to get results, and you're able to even not only get results, sometimes you're even able to, your imagination can take you further. I mentioned earlier these expansions in the dimension, or even treating theories as objects that can be manipulated, or treating Feynman diagrams as much more than just combinatorial objects that help you keep track of counting graphs, but as really describing a sort of history of a scattering diagram, describing the history in space-time of a particle. This becomes a tool, it becomes a powerful tool. It's very dangerous because once you accept that anything can be treated as anything else, of course, you can get nonsense as a result. But if you do this if you do this and you're a brilliant physicist, often it can give you very surprising results. More often than not, even for very good physicists, it gives you nonsensical results. But the few times when it gives something very impressive, and if you have the intuition and the nose to realize when it is, to realize when you are in such a situation, that's something that mathematicians have a lot of trouble accessing. What usually happens is the mathematician will be in awe of whatever formula you propose, and it will take 10 years to develop a framework that is completely roundabout from the physical point of view to make sense of that formula. And I guess that's all that's really all I meant to say. It's not, again, I think especially for analysis, it is very useful to, if you know analysis and you're very interested in physics, and you are curious not only about the mathematical results, but the physics that motivated them, knowing analysis can help clarify a lot of things, but I don't know a lot of examples where it has really changed things. Now, for statistical mechanics,
don't you agree that,
there are a few differences. I do think that
hold on, don't you agree that it allows you to actually solve the question? It allows you to actually verify that these models, what these models actually say.
It allows you to verify what these models actually say.
Yeah, like what is the behavior? Do you really? I mean, I feel like without the
yes, if you're interested in 100%, if you're interested in knowing what the logical, yes, that is mathematics. If you're interested in knowing what the logical conclusions of having set up the smallies, yes, by definition, that is mathematics. But
And
this
you
is
don't think
rarely
that
what.
that ever tells you something new that you didn't, that
No, it does. It does. I'm just saying historically, it has not. There are not many examples of this. There are not many examples where this rigorous approach has given results that people who have a physics approach to math could not have guessed.
could not have
That's
guessed?
really all I'm saying. Yeah, they could not have guessed. So I, there are examples. SLE was one of them, but there are just not many examples.
Where you don't know.
That's all.
I imagine they didn't know some of these critical exponents and SLE,
No, actually, no.
maybe from
That's unfortunately.
experiments they had seen it.
No, in fact, they had guessed it. Most of the critical exponents, and including some that could not yet be proved, they had guessed using completely non-rigorous methods,
Yeah.
using methods that, like conformal field theory, that are basically almost entirely based on this sort of, logical error that I'm talking about, where you allow yourself to treat everything as smooth functions and you don't care about whether Taylor expansions are convergent, and you manipulate and manipulate, and you don't even think. I think it's even more fundamental than this. It's not just, interchanging limits or differentiation and integration. Um, it's more that there are some fundamentally undefined quantities. They work with fields, and then they often, when you even ask what is the meaning here of the field, if I start with percolation and then I move to a certain field theory, what is the meaning of the field at this point X? What does it correspond to?
I understood
The
when
answer is
when people were talking about fields as sections of some kind of bundle over a manifold, so they transformed in a certain way, so you could write down the right. I mean, that made sense to me, but
yeah, so there's two different issues here. There's one, the issue of whether the field can be defined in a consistent way so that it satisfies the equations that physicists would like them to satisfy. That's a sort of analytic problem. That's this problem of divergences. But there's a separate problem, which is that in statistical field theory, you try to solve condensed matter problems or statistical mechanical problems by appealing to field theoretic methods. And what often happens in quantum field theory is it's no longer clear what is the physical meaning of the field.
hmm,
And in a lot of papers, for example, where field theory is applied to percolation, a lot of the original papers, although people are working on making all this rigorous, when people said, okay, now consider this field theory, it corresponds to percolation in some way, this correspondence was not even made precise. They just
what
say,
about
well, the field, if you calculate a certain correlation function, it should correspond to a certain probability that X is connected to Y, but this correspondence is not even made clear. So I think that
what about
that's more.
I've heard. I mean, I know that someone I knew at Columbia, this guy Clement Angler. Do you know him?
Yeah, yeah. So he is one of the people working on making various formulas in conformal field theory rigorous, but that's
Right, but don't you think that actually? What do you think of this approach? This actually makes sense to me.
it's
All
extremely, yeah,
these
it's
quantities make
extremely
sense on the
interesting.
discrete level. If you can, take a limit from the discrete to the continuous, maybe that.
Yeah, it's extremely interesting it's extremely interesting from a mathematical point of view. It definitely will help mathematicians understand field theory better. It is of interest also to very mathematically inclined physicists who spend a lot of time thinking about the mathematical structure of conformal field theory. I don't know that other than proving some formulas that physicists have already proved, they are producing many surprising results physically. Although again, because this is adjacent to SLE, it's possible that there are things here that I'm not aware of. But in terms of measurable results, there are not so many. And again, this is just a, I absolutely agree. If you ask me like, uh, let's take a much more basic example, much more basic that a lot of people can understand without thinking about advanced mathematics.
Mhm.
Suppose you look at electrodynamics. In advanced electrodynamics, you encounter all sorts of various solutions with various boundary conditions of the Maxwell equations. In most books, including
Very
graduate textbooks, the existence of those solutions, the asymptotics of those solutions are basically swept under the rug.
yeah.
Sometimes there'll be some explicit some explicit computations. There'll be assurances that things work the same way in the general case. But if you've taken a real analysis class and only afterwards you start learning electrodynamics, you'll start really getting very worried about the existence of various solutions. The how do you know that the generic solution behaves a certain way? How do you know that this expansion at infinity,
Yeah.
on which
This is my
yes, on which
concern in
yeah,
quantum mechanics, but yeah.
yeah, that say this, things at the radiation field. How do you know that all these things make sense? This by now is completely settled mathematics.
Mhm.
It is actually surprisingly advanced sometimes. Like for example, these things like the radiation field, the behavior of solutions for high frequency, they require some surprisingly advanced math if you're interested in the general situation where things cannot be written out explicitly. And I absolutely believe that if you understand this math, if you understand this PV theory very well, and then you learn electrodynamics, you will be much better able to build a coherent theory in your mind. And if somebody asks you, starts poking and asks you a few questions about things that are not so clear in the textbooks, you will be better able to answer those things if you do both things. But again, there's just an issue of
Even the
time.
treatment of the, frankly, even the treatment of the Poisson equation, just the way.
Yeah, absolutely. I completely agree. Even electrostatics, I 100% agree. You can easily catch, perhaps even working physicists in lies or not, you know, catch them in situations where they don't really know what's going on because they don't know this basic potential theory, or because they know it at what they call potential theory is not really what mathematicians call potential. But again, the return on investment is really,
Sure,
really
but
small.
that's okay. But
So
I know they have a different attitude. But maybe, how about this? What is your tool? What is the ace up your sleeve when you go to attack one of these problems, whether it's a probability or analysis? What theorem? What sort of technique do you have at your disposal? This is also for my own curiosity.
I mean, it depends on the field. It's often analytic techniques or techniques from basic PDE or stochastic differential equations. And in the case of percolation, I guess percolation is sort of its own field. It has mm, combinatorial aspects, but one thing that is very present in percolation, is, in addition to general probabilistic arguments, are what are called correlation inequalities. And so the question is, the day-to-day work looks like drawing certain diagrams, hoping that you can prove that these diagrams correspond to the generic situation using, on the one hand, basic probability, and on the other hand, correlation inequalities combined in various ways. So that would be for percolation. For random matrices, the type of approach that I've used or will incorporate tools from stochastic differential equations and the study of the relaxation of parabolic equations to their equilibrium states, and as well as some spectral theory. So they're very, I guess mathematical physics is perhaps characterized by a set of tools, so correlation inequalities, spectral theory, basic PDE theory. Those are definitely tools that are useful in many different areas of and also, I would say to some extent, analogies between different situations, for example, analogies between this infinite dimensional situation of trying to find an initial data for some function and a lattice model, but in both cases, you're looking at a Gibbs type measure. And even though they're very different situations on the face of it, certain symbolic manipulations, certain formal relations um, that are useful for the study of one Gibbs measure on one space can be useful also for other Gibbs measures in a completely different space.
Hmm. Okay,
All
I
right.
guess
Yeah. But
I don't know. I'm just thinking if I were to answer this question, in a field I used to work in, I just it's the maximum principle is the thing I'm always
yeah.
coming back
Yeah.
to, and you putting barrier functions underneath, trying to find the right thing to bound something else, that sort of thing. Uh, I don't know. I guess, and that I mean the physicists working in this area, if they're trying to answer some of the same questions, are not using those tools. right?
Physicists. So correlation, yeah, it's not. I wouldn't even say that they're not trying to use those tools. I think mathematical physics is a bit different in that physicists do use spectral theory. Physicists do use correlation equality.
Yeah,
It's
of
just
course
that
they know
the type of
the
things
value.
that they consider a result are different.
Hmm.
Meaning, on the one hand, the type of justification that they require, but also the things that they think are interesting. It's not so much the
Yeah,
tools that are different. Sometimes the tools are different because they, as I said, they don't care about exist. There's actually, I think, there's quotes of Witten saying he doesn't care about existence questions. That's why he's not interested in this Yang-Mills problem. Um,
uh,
but but
that's a,
what they consider a result because of the fact that they don't consider the same things to be important, surely the pools are going to vary a little bit. Because, for example, if we often use abstract topological fixed point type results to show existence of something. So these tools will not be so important to a physicist, but tools like correlation inequalities are tools that allow you to get bounds that could have a that can have a physical interpretation, they're definitely of interest to physicists, even if they are, quite advanced, if they're like Sobolev type inequality. But they have to have a physical interpretation. The bounds cannot just be whatever is required to apply a compactness result, or whatever is
yeah,
required to apply a soft uh, argument to get existence and uniqueness.
I see. I did not come here prepared with my arsenal of examples to, show physicists. Here's why you really needed to do math. That's never been. I mean, as much as I enjoyed learning about physics, just because I just want to understand some of the world around me, and because of the how varied the behavior is, and sometimes so complicated that we know that it's led to some very good mathematical models worthy of study. In my view, but I just take. I don't know that I'll ever improve physics. I just know how to deal with. If someone hands me the mathematical model that has structure and some flexibility, that's the thing I want to study. I won't try to get new information out of that using mathematical tools. That's what I understand. The what's important to a physicist, I don't. I guess I don't know anymore. I know historically what might have been important, but
Yeah.
why physics as opposed to I don't know the problems that come out of computer science or I don't know any other place where there's mathematical questions.
Yeah. I I think physics was a big source of problems, and physics is somewhat special in that physics is particularly mathematics has been particularly useful within physics. I think, for example, within biology, perhaps because we don't understand biology, perhaps because we have not identified the right models, uh, perhaps because it's harder to find the right models. So far, historically, um, mathematics has not been as the success of mathematics has not been quite as dramatic. I think it's not fair to use the success of mathematics within physics as a comparison for anything because famously mathematics for reasons for reasons that are not or that some people think are not very clear, but perhaps for historical reasons, because the mathematics was developed really towards most of mathematics, or a large part of mathematics was developed towards understanding physics, and we have not yet, um, even though mathematicians like to think of mathematics as something that is like, detached from base physical reality. At least there's a path dependent history here. At least the history of how mathematics has developed and patterns of thought and a lot of the tools that we have has been towards understanding physics. In other areas, it's not for lack of trying. For example, that people who've used it in biology, as I said, evolutionary biology, sociology, and even history, certainly
History, but
chemistry,
economics, it works.
economics. It has not been as successful. It has had limited successes, and people hope that one day it will be of the same, either hope or just hope against hope that it will, or that it already has the same power. But I don't think that's as I don't think it's as clear in these other cases.
It's true. You're sort of getting into a topic I know I wanted to talk about with maybe I had a different person in mind, but this question of the unreasonable effectiveness of mathematics.
Yeah, I don't really have very much to say about
And,
that.
and I know
I think
when you mentioned that there's some other quote, someone else, someone also, we should be talking about the completely reasonable ineffectiveness of mathematics in biology, uh,
yeah.
their
Yeah, I
perspective.
think that's I think I don't have great insight. I think I would have to think about more examples. It's a very the fact that it's such an oft quoted line
Yeah,
phrase means that there's definitely something there. Um, but for me, without thinking about it much more, as I said, that people find this surprising is what's surprising here. Because of course, to me, it's pretty clear that even if in principle, mathematics can, once you turn it into axioms and just logical rules, it can be detached from reality. Mathematics has a history, it has a culture, it has certain types of patterns. Recently, I was watching a mathematician, Kevin Buzzard, who's been I don't know how he pronounces his name, who's been very active in automated theorem proving and transforming known theorems into machine checkable proofs, and then with the idea eventually to feed those into AI systems that could help prove theorems that even mathematicians are not able to prove.
very
And
skeptical,
you
very
know,
skeptical of
he,
that
he also
enterprise.
he also he also mentioned that he was skeptical, but he's active in this area. And um, one thing I was thinking about that I did not think to ask at the end of the talk is um, once say machines suddenly start proving theorems automatically, how do we know what sort of things are actually interesting? There's a very basic problem that a lot of people have already anticipated. Maybe they come up with a proof of everything we ever thought about, like the Riemann hypothesis, but it's 1 million pages. And so it's completely useless to us. But even if Buzzard and his disciples are careful enough to make sure that everything is translatable back into a language that we can appreciate, these sort of theorems that we think are worthy of being theorems, that's 100% or not 100%. It's a largely human, you know,
I
endeavor.
agree.
That's why you have referees in journals, not so much to check that things are correct. Usually there are often mistakes, but usually things are more or less believable if serious people write them. But why do papers by top mathematicians still not get accepted at top journals automatically? It's because people disagree about what is worthy of proving. And what is worthy of proving is mostly worthy of proving for historical reasons, for reasons of taste, for reasons of what we think are difficult or is difficult, or what other people thought is difficult, or what famous people thought was interesting. And so for that reason, the fact that so much mathematics was developed with a view towards physics, perhaps less recently, but certainly in the 20th century, 19th and 20th century, um, makes it somewhat unsurprising that mathematics is extremely compatible with physics.
Hmm. I have not organized my thoughts on this subject just yet. I guess I have my own. I agree with what you're saying, and in fact, you seem to be saying things that strike a dagger into the heart of those people who really want to say mathematics is so pure and really discovered, because you're talking the very contingent, the path dependent way that mathematics develops.
Yeah, this seems to me very, very clear. Again,
Yes,
in principle, it could be, you could say, well, this is just a set of axioms. Anybody who believes in these few logical rules would come to the conclusion. But of course, that is largely nonsense, because why would you want to, develop something like spectral theory? Why would you want to study certain types of questions rather than others? That, of course, is dependent
I know how
on
we
history.
got to eigenvalues, eigenvectors.
Yeah, well,
People
well,
knew
I
those
mean,
were important at the time that they were set up the models where that
exactly. So yeah, for quantum mechanics. All right.
Um,
Do you? I'll have to go in maybe 10 minutes. Do we
uh-oh.
attack maybe another subject, or like if you had any final subject that you wanted to talk about?
Oh, well, I had lots of other stuff about that were not strictly mathematical. Are you so you are happy to be a math professor? That is, you are going to be the head of the Cornell math department someday?
No, I hope not. I think I'm not so interested. I like the contact with students. I'm not so interested, at least for now. I think things can definitely change in the future in administrative tasks. But I do think that, again, I do think that can change after a while. Maybe
I guess by
you
head, I only meant the maybe the most prominent person, and also maybe driving the development either of math or of the department in some way.
Yeah, for me, I guess I already hinted at this earlier. I don't really have this deep or almost mystical either admiration or connection to mathematics. I just like it. I like doing problem solving, and I like learning about math also. I like discussing math with people. It does. I think it does. Especially since I'm interested in some more technical areas of math, it does provide some clarity when you try to learn about other areas like economics or physics or other areas where that are known to be technical, but in my estimation, the technical parts are rather easy once you come from a mathematical perspective. But yeah, I don't have very grandiose aspirations as a mathematician. I just think it's a very exciting mathematical research is very exciting. It can be an emotional roller coaster, um, and
Yeah,
that's
I
something I
agree.
enjoy. That's something I enjoy. I also enjoy the you know the I don't know if it's quite social because it's often your group of collaborators is a rather restricted social environment, but I enjoy exchanging exchanging ideas with other people about math and just the process of coming up with a solution to problems which, at least to you initially, seemed the solution seemed quite far out of reach.
Do you have any sense of what should students in math learn
Oh yeah, I don't know.
or not learning, or
I was quite happy, and I think, and certainly biased because of it. I was quite happy with my own undergraduate education. I went to McGill, and I think their undergraduate honors program, being a Canadian university, it was a quite hefty program because Canadian students typically take classes in just one or two subjects. There's no breadth requirements, so the typical math students at McGill took mostly math classes, and that included several.
you know you
Sorry,
Wong?
you won't. Yeah, I know him. I know he was in my year. He graduated the
Oh, you,
same year as I did. He was in several of my classes. So that curriculum included four algebra classes, four analysis classes, classes in PDEs and differential geometry, and
that's a serious program.
yeah, complex analysis. Yeah, it was definitely a well-rounded program. It's probably too much for a lot of American students because
It's
just because
more
of
than what's at Cornell, right?
quite possibly. But again, I think this is because of this difference in point of view on what an undergraduate education should consist of.
Uh, it's such a shame that that you have to go so soon. We started. I like how we did things here. I don't know how much a lay audience will get, and this is sometimes difficult for me. I'm not an expert in your field. I don't know why I thought I could try to talk to you on your level about your field, but we got into there. There's some important philosophical issues I didn't know would necessarily come up about the difference between math and physics, and exactly what sort of role math plays there, and how math is done, what is important, that I really want to get into some more if we did this again.
Yeah, that could be an idea
I did not
if you have
start
time.
out the way I've seen a lot of other podcasts. Lex Friedman always has a guest that he's like, is there life on other planets? Is mathematics invented or discovered? What is ultimate truth? I don't know. I'm not. Maybe I'm putting in Lex Friedman with some other people of podcasts, and I didn't just want to hit those things that I like people talk about. But if anything that we talk about, can we really add to that conversation? I wonder.
I think we actually spent quite a bit of time on it. I think the yeah, I was happy that you asked about. Uh, I had heard your point of view on math and physics before, but I was happy to have that conversation again. It's quite a deep question, and honestly, in general, I'm quite skeptical because I'm aware of my own limitations of very, these sort of deep questions and, completely freewheeling discussions of them, although I guess we've been talking about them in a very freewheeling way for quite a bit. Um, but yeah, I, um, I think it can be interested. It can be very interesting, but I think these are the types of discussions that are often more interesting when you either are part of them or perhaps when you listen to them not too carefully than when you really start analyzing them. Because I feel
Well,
like,
I know that when that guy, oh, now I'm Yuri Milner, when he created this breakthrough prize, he gave it to those
mhm,
5 people. He wanted to be the moderator. He brought them up on stage, and he immediately just asked, like, take 5 giants of mathematics and ask them, is mathematics invented or discovered, and what is ultimately true? Why is what explains that math describes the universe and all of this kind of thing? I don't know. Were these people any better able to do it than any other mathematician, or maybe some philosopher who's thought about this? Uh, Hard questions. Let me ask you one different question, and if there's a short answer, you can give it. If it's a longer answer, maybe we just have to have another conversation. Why be a math professor at Cornell when you could take your knowledge of probability and make a lot of money? Uh,
um, yeah, so I think I actually, I guess there are a few answers. One could be simply that I quite enjoy what I'm doing. Perhaps a more cynical answer is that I think professors are already paid quite a bit, so I'm not at want
enough
for
of your
anything.
day.
So I don't know if I would have, the answer I gave before is sincere. I actually really enjoy mathematical research. If things were materially much worse, I don't know if my answer would be the same, but it so happens that they're not. And so there's not, I don't really have, I don't really, there are not many things that I can think of that I would really want to do that I'm not able
That
to for
townhouse,
material reasons.
in Manhattan, like Jeffrey Epstein had.
No, okay. So when I say there are not many, I can most definitely think of things that material things that I could want, but whether I really need them and whether they would really improve my life for longer than the few weeks that it takes to get over the initial the initial satisfaction of having acquired something.
Hmm.
I'm not so sure about. So I think you know you know, satisfaction is pretty hard to attain, and if you're happy enough with something, your position in life, you should think about whether you really want to make drastic changes, uh, whether it's worth your time. You don't have um, unlimited amounts of time, so that resource should really be conserved and economized as much as possible. And I don't think, for me at the moment, it's worth spending very much of my time to acquire more, you know,
Is that
material
from
goods.
experience of knowing? That sounds like some wisdom, but you really know what you like, you really
I've
know
not.
what things to do. But
I,
have you had that thing though? I wonder.
yes and no. I've never had, I've never been extremely rich, but I've always been very I've never been at want for anything. I've had, I've been lucky to, to have studied in the U.S. and before that in Canada, to having born in Switzerland and grown up in Luxembourg, all very rich countries. So even though my family was never particularly wealthy, relative to wherever they lived, in absolute sense, I think we were doing extremely well. So that definitely, if again, if things had been much worse for me all my life, certainly this would have colored my aspirations. Um, so to answer directly what you said, I don't have a point of comparison at the level of ultra wealth, but from what I've seen of relatively wealthy people, or what I've seen from of relatively wealthy people has not been sufficient to entice me to, chase uh,
Hmm.
much more than what I have materially.
Interesting. Whereas I love math. But I also want a lot. Uh,
Yeah, you're in good company.
yeah, and also it's good that you have a job. You have your professor. It's very difficult to get.
Yeah, so as I said, it's easy for me to say that I'm satisfied. I have been very lucky.
All right, very good. Uh, let's talk again and
Yeah,
pick up some.
certainly.
I didn't even ask you. I know nothing about Switzerland or Luxembourg. Uh,
Yeah, that's a good topic for an upcoming conversation.
all right, great. Thanks so much.
Yeah, thanks for talking to me. Thanks for having me. See you soon.
Great.